That's good. So let us start the lecture. Okay, that's it. So the lecture number 2 is about conjugate distributions and Bayesian linear regression. Do you see the slides, guys?
Yes.
That's good. Again, please don't hesitate to ask questions. In case something is going wrong, I don't know, with whatever, with slides, with you don't hear me well, you also can ping me in Telegram, in chat. So let me just in case open the chat. Second. Okay. So let's start the lecture. Today we'll discuss conjugate distributions, and also we'll discuss the the very basic model, Bayesian linear regression. Of course, everybody knows linear regression, how it is defined. But using this simple linear model, it is possible to demonstrate explicitly, the main ideas, approaches for Bayesian modeling. First of all, let me start from some basic properties of the Gaussian distribution. I will use these basic properties for many times for obtaining explicit formulas to calculate the posterior distribution. First of all, this is the standard definition of the one-dimensional Gaussian distribution. This is the definition of the two-dimensional Gaussian distribution. So the density of the Gaussian distribution is given by this formula here. Mu is the mean vector, and sigma is the covariance matrix containing values of covariances between components of the vector x. Actually, the covariance matrix, it defines the shape of the distribution, the shape of the support of the distribution. If we calculate eigenvectors and eigenvalues, then the typical size of the contour lines of the distribution, these sizes, they are proportional to the corresponding values of eigenvalues. Like if the maximum eigenvalue is 2 times bigger than the second eigenvalue, then the size of the ellipse along the first eigenvector is 2 times bigger than the size of the ellipse along the second eigenvector. And this holds true for any possible contour line. Orientation of the ellipsoid is defined by the eigenvectors. And this is the property which we will use throughout the course. Let's imagine that the vector x is distributed according to the multidimensional Gaussian distribution with the mean vector mu and the covariance matrix sigma. We divide the vector x into two subvectors. The first subvector we denote by x sub a, the second subvector we denote by x sub b. It's obvious that each of these subvectors is distributed also as a the distribution of each of these subvectors is also Gaussian. And so we divide the mean vector with respect to in the same way. The mean vector mu is divided into subvector mu sub a and the subvector mu sub b. And the covariance matrix sigma capital is divided into four submatrices, sigma capital AA, AB, BA, and BB. These are covariances between components of these two subvectors. And the property is as follows. We can prove that if we consider the conditional distribution of the subvector x sub a given the fixed value of the subvector x sub b, then this conditional distribution is Gaussian with the mean value given by some mu and the covariance matrix given by some matrix sigma capital, where these two quantities are defined according to these formulas. So let me briefly explain the main idea. Because two subvectors x sub a and x sub b are correlated, the covariances between components of these two subvectors are non-zero. It's obvious that if we know some values, some specific values of the subvector x sub b, this should influence somehow the distribution of the vector x sub a. And so the distribution of the vector x sub a is again Gaussian, but the mean vector of this subvector is shifted, and this is the value of the shift. It is proportional to the value of the subvector x sub b. And the weight here is depends on the covariance submatrices. Moreover, because the submatrix sigma capital AA here is positive definite, and these covariance matrices here are also positive definite, then here we have the difference between two positive definite matrices. And so in some sense, because we know some information about the exact values of the subvector x sub b, we reduce the variation of the subvector x sub a. That is, the uncertainty of the in values of this vector x sub a is smaller than the uncertainty of this subvector in terms of defined by the unconditional distribution. This is the illustration. So this is the unconditional distribution of the joint vector xa and xb. And when we fix some specific value of x sub v, then that means that we consider the distribution of the vector x sub a only along this line. And so this distribution here is equal actually by the projection of this distribution mass under these constraints. And this is what we get. It's obvious that the variance of this projected distribution is smaller than the variance of the unconditional distribution. So we will use this formula many times. And here is another more general property. If we have some vector z, random vector z with Gaussian distribution, and the parameters of this Gaussian distribution are given here, and also the value of the vector y depends linearly on the value of the vector z, such that the mean value is given by this formula and the covariance matrix is given by this formula. So we can prove that the unconditional distribution of y is given by this formula. So the variance, of course, is higher because, okay, the distribution of y given z is this, but z itself has some variation, right, due to randomness. And so we just need to sum variances, initial variance of y given z and the variance due to variation of z. Also, we can use a standard Bayesian formula to calculate the posterior distribution of z given y. And here is the formula, where the matrix sigma capital is given by this expression. I'm not providing here any, proofs because these proofs are very simple and technical. You just need to use Bayesian formula, consider the exact expression for the Gaussian multidimensional density, and that's it. You manipulate with terms and you get this conclusion. Any questions so far, guys? Okay, there are no questions. I hope that everything is clear. Now let us discuss conjugate distributions and why do we need these, the idea of conjugate distributions. First of all, most of distributions we consider in daily practice, like Gaussian distribution, exponential distribution, Poisson distribution, and other distributions, actually they belong to so-called exponential family of distributions. So exponential family of distributions is given by this formula. So this is a general expression. And actually, if we consider different specific expressions for the function h of x, t of x, and a of theta, we will get exact, we will get different expressions of particular distributions like Gaussian distribution, Poisson distribution, and other distributions. Here, t of x is called a vector of sufficient statistics, and a of theta is called cumulant generating function. Actually, a of theta, it is a normalizing constant. Because the integral of this expression with respect to x should be equal to 1, because p of x is considered to be a density function. And so we need some normalizing coefficient, which of course depends on theta, so that this integral is exactly equal to 1. That is why a of theta is the normalizing coefficient, but we, we define it in this way, and later it will be I will explain why. First of all, let's consider normalization. So what is normalization? Because p of x is a density function, the integral of p of x dx should be equal to 1. This is the expression for the integral. And so we see that the function exponent of a of theta is equal to this integral. And it's obvious that, for example, if t of x is equal to x, then e of theta is the logarithm of Laplace transform of the function h of x. By the definition. That is why a of theta is called cumulant generating function. Anyway, a of theta defines the normalization, and later I will also show you some properties of this function. These are examples of distributions belonging to the family of belonging to the exponential family of distributions. For different functions, a of theta, h of x, t of x, we can prove that from this general formula here, we can get any of these one-dimensional and multi-dimensional distributions here. And the question is, why this is so important? Before going into detail, let me explain how we can prove the fact I mentioned. So this is the general formula. Let's consider, for example, so-called Bernoulli distribution. Here, alpha is the probability of success. So if the input variable x is equal to 0 or 1, then the probability of x equal to 0 is equal to alpha, and vice versa. So we can rewrite the expression for the Bernoulli distribution in this way. That's it. So we see that if we define theta as a logarithm of this ratio, and a of theta we define equal to this guy, then in this case, for such functions t of x and a of theta, we get exactly the Bernoulli distribution written in this form. Let's consider the case of the Gaussian distribution. The situation is the same, so we open brackets here. We define statistics t of x equal to x squared. So now this statistics t of x isn't one-dimensional, it is two-dimensional, and the vector of parameters theta is also two-dimensional. The function a of theta is equal to this guy, and because we define parameters theta in this way, we can rewrite the function a of theta in this way. And so this is how we prove that, for example, the Gaussian one-dimensional Gaussian distribution belongs to the exponential family. In this way, you can prove the same thing for all other distributions in the same way. And now let me explain why the exponential family of distributions is very important. Actually, in some cases, it allows to prove exact formulas for the posterior distribution, straightforwardly. So what is posterior distribution? As I explained you in the first lecture, if we have some vector of parameters w, then because we don't know the vector of parameters w, we impose some prior distribution p of w. P of x given w is the likelihood function, and the posterior distribution is given by the Bayesian formula. Denominator isn't a function of w, so it's just a normalizing term. The question is, imagine that we have some specific parametric prior distribution for the vector of parameters w. And also we have some specific parametric family of likelihood functions p of x given w. When we multiply this likelihood by this prior, to which family of distributions this product will belong to? And actually, conjugacy means that if p of w and p of w given conjugacy means that if p of w belongs to some specific parametric family of distributions, then it happens that p of w given x will belong to the same family of distributions. For example, if p of w is Dirichlet distribution, and the likelihood function is given by the multinomial distribution, then the product of the multinomial distribution by the Dirichlet distribution will result in a posterior distribution which will belong to the family of Dirichlet distributions. So that means that we don't need to calculate anything explicitly. We already know from the very beginning that if this happens, if these two things happens, then the posterior distribution will be a Dirichlet distribution. And from this fact, we can easily calculate parameters of this Dirichlet distribution. And this is quite simple. If this happens, then P of W and P of X given W are called conjugate distributions, because they are, when we calculate the posterior distribution for the conjugate distributions, the posterior belongs to the same family of distributions. And this is exactly what happens for the exponential family of distributions. Let's consider the example. P of W is, imagine that the prior distribution on W is given by the Dirichlet distribution. The density of the Dirichlet distribution is given by this formula. And as I said, the likelihood function is described by the multinomial distribution in X. This is the formula for the multinomial distribution. This is the standard multinomial distribution. And so what we get when we multiply the multinomial by the Dirichlet, we get the distribution which is equal to the some constant value. So this is the normalizing constant. And we don't want to calculate it because, okay, we don't need it because we already know that this distribution should belong to the family of Dirichlet distributions. So the main thing here is this product. And we see that with respect to the parameter W, with respect to the argument W here, the posterior distribution depends on W in this way. Here is it. And if initial parameters of the Dirichlet distribution were given by alpha, now the parameters of the Dirichlet distribution are defined by X plus alpha. That's it. But because this is the Dirichlet distribution, and we know how the normalizing constant is defined for the Dirichlet distribution, we can estimate the normalizing constant immediately. So instead of parameters alpha here, now we have parameters X plus alpha here. That's it. So we just, the normalizing constant is given only by this way, is given only by this expression. That's it. So again, we consider the exponential family of distributions only because for the distributions from this family, we can calculate the posterior in a very efficient way. We know what kind of posterior we get, and we don't need to explicitly calculate the normalizing constants because of this fact. That's it. Another example, so if the prior distribution is Gaussian and the conditional is Gaussian, the posterior will be also Gaussian. If the prior is beta, if the likelihood is Bernoulli, then the posterior will be also beta. Dirichlet, multinomial, we also get Dirichlet. If we consider prior distribution inverse Wishart distribution as a prior on, say, covariance matrix, and we consider Gaussian distribution as likelihood, again, as a posterior on the covariance matrix, we get the inverse Wishart distribution. This is the general formula. So conjugacy is mutual, that is Dirichlet multinomial Dirichlet or multinomial Dirichlet multinomial. That's it. And so in all other calculations, we will use these two important properties. Like the first property is how to calculate the posterior distribution for the Gaussian family, or how to calculate the conditional distribution of the Gaussian subvector given other subvector. We know the explicit formula for this, and how to calculate the posterior if the distributions belong to the exponential family if they are conjugate. Any questions so far, guys? So everything is clear, no questions. Well, that's good. Before going into details with the Bayesian linear regression, let us discuss the general definition of linear models, because I will use these definition throughout the lectures. So linear basis function models are given by this formula. We assume that we somehow convert input features x into some basis function values. And we consider a linear combination of these basis functions. So by phi of x, I denote a vector of known basis functions, and w is a vector of parameters. As a typical basis functions, I can consider some polynomial values, some powers of input features. I can consider Gaussian functions, radial basis functions, so-called. In this case, I assume that the coefficient, the center of the radial basis function is somehow fixed, and the scale of the radial basis functions is also somehow defined. Or I can consider, say, sigmoid function, for example. Also, I assume that the parameters of the sigmoid function are somehow defined and fixed. First of all, before going into detail with the Bayesian linear regression, let us discuss how we define the likelihood for the linear model, and let me explain how why the likelihood maximization is equivalent to the so-called least squares problem. So data model for the output value y is given by this expression here. We assume that our observation of y is equal to the value of the function f of xw plus epsilon, where epsilon is a white noise. For this white noise, I assume that it also has a Gaussian distribution. That means that the distribution of output, given values of x and w and parameter beta, where beta is the variance, it defines the variance of the white noise. So the distribution of y given x is given by the Gaussian distribution with mean value equal to this and variance equal to this. Let us denote by y capital M a set of observations, of output observations, and by x capital sub M a set of input vectors. And this is the data likelihood. That is, because all observations are considered to be independent, identically distributed, the likelihood of the data set is equal to the product of individual likelihoods for each observation, for each separate observation. And for each separate observation, the likelihood is given just by the Gaussian density, with the mean value equal to this guy. So this is just the value of the linear basis function model. And this is the variance due to white noise here. That's it. So this is the exact expression. Here by n, I mean the density of the Gaussian distribution. Data log likelihood has this form, so I take the logarithm. Here I get, instead of the product, the sum of individual log likelihoods for each individual observation. And because here n is the density of the Gaussian distribution, when I plug the expression for the density of the Gaussian distribution, I get this expression. So it's very simple. Here, m is the number of sample points, and E of W is the sum of squared residuals, where residual is equal to the difference between the output value and the prediction according to the linear basis function model f of xw. So it's obvious that in order to estimate the parameters of the function, we need to estimate W by maximizing the log likelihood. But in this expression, only the last term depends on W. So maximization of the log likelihood is the same as minimization of the sum of squared residuals. This is the equivalence. And this happens, of course, only because of the assumptions. The first assumption was that and the main assumption here was that the white noise here has a Gaussian distribution. Because of this, we get this equivalence. So maximizing log likelihood, it is the same as to minimize the sum of squared residuals. And from the course of machine learning, we know that minimization of the sum of squared residuals leads to the following expression for the optimal value of parameters W. So F capital here it is a matrix containing values of the basis functions evaluated on sample points x sub I. So it is the matrix of size m small by m capital. And if we maximize this log likelihood here with respect to beta, we will get the following expression, the following maximum likelihood estimate for the variance of the white noise. As you know from the course on machine learning or statistics, besides the standard least squares regression, there exists so-called regularized least squares regression. Regularization means that besides minimizing the sum of squared residuals, we also minimize an additional term which defines the regularization on the vector of parameters W. This vector of parameters W is given by the second norm of the vector W. So we minimize with respect to W this expression. And the solution has this form here. The only difference with respect to this formula is that here we have this additional term. And so if the matrix phi transpose phi is ill-posed, thanks to this positive definite matrix here, we always can invert this matrix and get a stable result. That is why this expression is more preferable to use in practice to estimate the coefficients W. Now let us consider the definition of the Bayesian linear regression. So before I just discussed the standard linear regression model under standard statistical assumptions, which is often used in mathematical statistics. But now I'm going to discuss a little bit different interpretation of the regularization and what kind of benefits we can get from this interpretation. So again, we have a data sample XMYM, and we assume that this sample is generated by a linear basis function model. So that means that the output Y is equal to the linear basis function model plus white noise. And the white noise is assumed to be Gaussian. And so, as explained in the previous section, the likelihood of the data set given the vector of parameters W is equal to the product of individual likelihoods of each observation with the mean value given by the linear basis function model. And in the matrix form, this likelihood is given by this formula. So this is the vector of mean values. And because all observations in my data set are assumed to be identically distributed and independent, that means that the covariance matrix of the Gaussian distribution is diagonal. And so here we get, that is why here I wrote this value. So again, all output values in my data set is distributed, has Gaussian distribution with mean value given by this linear basis function model and covariance matrix given by this diagonal covariance matrix. A typical prior which we will use in practice is Gaussian. Well, it's because it's always, useful and efficient in terms of getting explicit formulas to consider a Gaussian prior, right? So because for Gaussian prior we know everything, and Gaussian likelihood with Gaussian prior are conjugate, so we can easily calculate the posterior. As you remember, in the very beginning of this lecture, I told you that if the distribution of z is Gaussian with these parameters, if the distribution of y given z is Gaussian with these parameters, then we get that the posterior distribution of y of z given y is also Gaussian. And the parameters and the explicit expressions for the parameters are given by these formulas. And so this is why if I assume that the distribution of data given W is Gaussian and the prior distribution of W is Gaussian, then it's obvious that the posterior distribution of W given data set is also Gaussian. Using these formulas here, I can calculate explicitly the mean value and the covariance matrix of the vector of parameters W. They are given by these expressions here and here. That's it. Very simple. Let's look in more detail to these expressions. It's obvious that this expression here, it is almost exactly the expression which we got in case of the regularized least squares regression. Why? It's because matrix SM here, it is equal to this, and so this expression here is beta multiplied by alpha minus 1 I. So this is can be considered as a kind of regularization, plus beta phi transpose phi to the power minus 1 second, multiplied by phi transpose y. And so this is, almost the same as in case of the standard linear regression, regularized linear regression, except this additional normalization here and here. But of course, but it's obvious that this doesn't, change anything. And so this means that the Gaussian prior distribution on the vector of parameters W, it is equivalent to using the L2 regularized linear regression, because the estimates we get, they are very similar. I mean, they're almost the same. And now let us consider how we can, interpret this formula. So now I'm going to show you the recalculation of the estimates step by step. So I have some sample of the observations, and I get one observation at a time to update my, estimates of parameters. So let's assume that I consider a model, a simple linear model with only two parameters, W0 and W1. This is the prior distribution for the parameters W1 and W0. So a simple Gaussian prior. These are contour lines of the Gaussian distribution. And if I generate any pair of values of parameters W0 and W1 from this prior distribution, then I can plug the generated values inside this linear model, And here I depict the linear models corresponding to different values of W I get when I generate W1 and W0 from these prior distribution. And so these are possible linear models with W1 and W0 generated from this prior distribution. Nothing interesting, right? Then I got just one new observation. So this is my observation. Oh, sorry. This is so I got one observation. Let us write it like so. I get one observation x1 y1, and then what I can do, I can write so-called likelihood for this observation. So this likelihood for this observation, it is given by the Gaussian distribution with the mean value equal to V transpose multiplied by x1, and here I have 1, and the variance, and by this variance. Here is it. And so when I consider the logarithm of this Gaussian density, this is some function of two parameters, W0 and W1, right? And so here I depict, this is how this function g of W1, W0, W1 depends on parameters W0 and W1. This is it. Then what I do, then I take this likelihood for only one observation, and I calculate the posterior. This is the posterior of the parameters W1, W0. And so it's obvious that because this likelihood just for one observation, it behaves like this. So the most of the probability mass is concentrated along this diagonal. So when I multiply this prior by this likelihood to estimate the posterior, this likelihood cuts the probability mass in this region and in this region. And so now my posterior is concentrated in this way. So now if I calculate values of parameters W1, W0, and sorry, if I generate now the values of parameters W1, W0 from this posterior, and for different values of W1, W0 generated from this posterior, if I draw plots how this linear function behaves, I will get these plots. And by blue here, I depict the one observation for which the likelihood looks like this. This is just my observation. Okay, this is the first step. On the next step, I got the second observation. And this is, again, the likelihood just for one new observation which I got on the second step. So this is the likelihood just for one observation. In order to calculate the posterior of the data set, of the vector of parameters W given the data set, I need to take the posterior from the previous step and multiply it by the likelihood on the second step, right? And because the likelihood on the second step looks like this, so it cuts the probability mass of this posterior in this region, right? So it destroys probability mass here and here, because okay, here the probability mass is 0 and here the probability mass is 0, right? And so now I see that when I multiply this posterior by this likelihood, by this new likelihood for one new for additional new observation, I get these posterior on the second step. And now, if I calculate if I generate values of parameters W1 and W0 from this posterior and draw the corresponding linear models, my function, my linear models will behave like this. By blue points here and here, I depict these two observations I have, for which I calculate these, actually calculate this posterior. On the third step, I get the third observation. The likelihood for this third observation behaves like this. And so when I multiply this posterior by this likelihood, my posterior on the third step is concentrated even more. And now we see that I can estimate values of parameters W0 and W1 very accurately because the posterior is very concentrated. And so it's obvious that now if I get more and more observations, then my posterior is concentrated more and more across around some specific value of parameters W, for which and if I generate values of parameters W from this concentrated posterior, I will get almost the same values of W, so that the corresponding linear models will behave, you know, very. Their behavior will be very similar. That's it. So you see how the Bayesian approach works. We get one more data point. We update the posterior starts to concentrate more and more. At the same time, because the posterior has some probability mass around the most probable points, this probability mass around this domain of definition of the posterior can be used to estimate the uncertainty of the decision. And this is the important benefit of the Bayesian approach. We can obtain not only the point estimate, but also we can obtain the estimate of the uncertainty. Any questions, guys, so far? Do you hear me?
Yes.
Okay, I hope that everything is clear then. And now let me explain how we calculate, how we make predictions in Bayesian case. So this is our posterior of W given the data set. Alpha and beta are parameters. So alpha is the parameter of the prior distribution, and beta is a parameter. It is the parameter which defines the variance of the noise. In order to calculate the prediction of y given x, what I do, I need to integrate out the parameters which I don't know, because I don't know the parameters w. So and all information about the parameters w is contained in the posterior distribution of w given the data set. So I take the predictive distribution P of y given x w, and again let me remind you that the predictive distribution here's it. The predictive distribution of y given x w is given by the Gaussian distribution with mean value defined by the linear Gaussian by the linear basis function model, and the variance defined by the parameter beta. So what I do, I take the posterior distribution over the vector of parameters w, and I integrate out the parameter w with respect to the posterior distribution to get the prediction, the distribution of y given x. That's it. Okay. So this is the formula. Here the distribution is Gaussian with the vector x and the vector of parameters w, and this is the distribution, the posterior distribution of w given the data set. So I just proved in the previous slide that the posterior distribution of W given the data set is Gaussian with mean value given by some vector of parameters omega, and the covariance matrix given by this formula. This is what we have proved. Because the distribution of y given x is also Gaussian, and again, here the function f is linear with respect to the vector of parameters w. It's obvious that when I integrate the Gaussian distribution with respect to mean, which depends linearly on the vector of parameters w, and I integrate this with respect to the Gaussian distribution, then I again will get the Gaussian distribution. And it's obvious that the mean value of this Gaussian distribution will be given by the mean value of this posterior distribution P of W multiplied by the vector of basis functions. So this result here is quite obvious, I think. But what is not super obvious is the posterior variance of the predictions. And the posterior variance of the predictions, it is given by this formula. So we see that we get this variance. This is the noise variance, right? And this is the additional variance we get because we don't know the values of parameters W exactly. There is uncertainty in the values of parameters W. And this is how we estimate this uncertainty in predictions resulted from the uncertainty in the values of parameters W. Fortunately, in case of linear models, we can calculate these explicitly. In case of deep neural networks, it's not possible. And so we will have to use various types of approximations. And also we can, the posterior mean here, this posterior mean here, can be used for point prediction, and this posterior variance here can be used for uncertainty estimate. So let's consider an example. This is here by blue points, I depict our one observation. Green is a real function which generated a sample. So using this one observation, I calculate the posterior mean and the posterior variance. Because I have only one observation, the posterior mean is almost equal to 0, and it is given here by this red line. The posterior variance given by this formula here, plus minus sigma, it depicts this pink region here. And it's obvious, and we see that, okay, because we don't have any points here, the uncertainty here is big. When we get the second point, we recalculate the posterior mean, and we observe that now the posterior mean is already close to the original function, and the variance around the second point and the first point, the uncertainty is reduced. But still here uncertainty, and here the uncertainty is big because we don't have any observations here. As soon as we get more observations here and here, the posterior mean is updated, and now it is even closer to the true function, and the uncertainty around this point and this point is also reduced, although here and here the uncertainty is big. And as soon we get more and more points, we reduce uncertainty everywhere, and so now the posterior mean quite nicely approximates the true function, and uncertainty is quite small, so now the uncertainty is almost equal to the true noise. So because we don't have, we almost don't have any uncertainty in the values of parameters. That's it. Also, what we can do, because this is the predictive distribution, we can sample, we can sample trajectories from this predictive distribution. We sample vector of parameters W, and with this vector of parameters W, we can sample the trajectory of the possible function, right? And so how, let me demonstrate how it looks like. This is our observation, the only observation. We take this observation and we sample the values of parameters W from the posterior distribution given the data set. And then we take this sampled value of W and draw how the function f of xw looks like. And we see that because we have only one observation, the trajectories of this function, they're quite random, right? If we have 2 points, now the trajectories of this function for different values of parameters W generated from the posterior, now the trajectories are less random. But if we draw, if we get more points, the trajectories are even less random. And when we get a lot of sample points, the posterior is concentrated, and so the vector of parameters W generated from the posterior distribution is almost is very close to the true vector of parameters W. And when we generate the trajectories of the function with such values of W, they are very close to the true function. That's it. Any questions so far, guys? Everything is clear? No questions?
Evgeny, one small question. What strategy can we use to select the sample points? So we can use the variance, or they may be more complicated strategies.
Well, the simplest strategy would be to select the next point so that it minimizes it maximizes the variance. So you select such point where the variance is maximized, and when you sample this point, you will reduce you will get the information in such region in which initially the variance is too big, right?
Yeah.
So this is the simplest strategy. But of course, we can consider different strategies. We can, for example, calculate average variance and maximize and minimize the average variance. We can calculate predictive error and maximize the predictive average error. I would say that in practice for standard Gaussian process model, and actually in some next lectures we will consider the Gaussian process model. So for the Gaussian process model, such strategies are quite close. So they provide quite similar results. And so the simplest strategy is just to use the first one, maximize the variance. But in some cases, you can get better results with other strategies. So if you want, I can send the link to the paper where all the strategies are considered and evaluated.
Thank you. This is very interesting.
Okay. In the end of the lecture, I'll send in chat the link to the paper. Okay. Now let's consider so-called evidence approximation. Guys, so we discussed that the predictive distribution of y given x is given by this integral here. The only problem is that in order to make predictions, we need to know parameters alpha and beta, right? But how to estimate these parameters? And for this, we can introduce also hyperprior on the unknown parameters. So if there are some parameters and we don't know these parameters, let's introduce prior on them and calculate the posterior. This is the typical Bayesian approach. So we introduce some hyperprior over parameters alpha and beta, and we calculate the posterior over alpha and beta given the data set. In this case, in order to estimate the predictive distribution given x and the data set, we also need to integrate out these unknown parameters with respect to this posterior distribution. Well, the concept is looks quite nice. The only problem is that in practice, even in case of linear regression, it's almost impossible to exactly calculate the posterior distribution of alpha and beta given the data set. So it's not possible to estimate this integral, especially in case of neural networks. This is impossible at all. And so the question is what to do. We assume that the posterior distribution here, it is sharply peaked. So if this is the value of parameters alpha, we assume that we have enough data sets, so this posterior distribution is sharply peaked around some specific value of alpha hat, right? And so and the same happens with the parameter beta. And so in practice, the only possibility is to not to integrate these parameters alpha and beta with respect to the posterior over alpha and beta, but we can estimate the most probable values of alpha and beta and plug in this value, these most probable values of alpha and beta in our formula. That's it. This is how we act. The question is how to estimate the most probable values of alpha and beta. According to the definition, the posterior distribution of alpha and beta given the data set is proportional to the likelihood of data set given only alpha and beta and multiplied by the prior on alpha and beta. Let's assume that the prior distribution here is almost constant. So this is the assumption. Like this is alpha and the prior distribution over alpha is is almost uniform. So this function, it doesn't depend on alpha and beta at all, or depends on alpha and beta, but depends quite depends not significantly. So in practice, this is called so-called flat prior. If the prior is flat, that means that the prior doesn't depend on the value of parameters. And so the most probable values of alpha and beta with respect to the posterior distribution is this, because this prior doesn't depend on alpha and beta, it is the same as to maximize this likelihood of data given alpha and beta. In order to obtain, in order to solve this optimization problem, there exists a special iterative optimization algorithm. We will discuss this algorithm later and also in the seminar. And now let me briefly explain how we can estimate this function, how we can estimate this function here. So this is the likelihood of data given alpha and beta. What is it? This is the likelihood of data given W and beta, and we integrate it with respect to the prior distribution of W. So we need to take the likelihood of data and we need to integrate the likelihood of data with respect to the prior distribution. That's it. How we can do this? Let's introduce the following notations. This is the function E of W equal to this function is a quadratic form of W, and it is given by these two and it is given by these two functions here. Okay, unfortunately here it is a kind of misprint, so here it should be W. So this is the sum of squared residuals, right? So the difference between the output values and the linear predictions, and this is the L2 regularization. Since this Gaussian distribution, since this likelihood distribution likelihood function is Gaussian. It is given by the Gaussian distribution. And because the prior distribution is also Gaussian, and quadratic forms of this Gaussian distribution are given by this function and this function. So I will yeah. So what we get, it's obvious that when we plug the expression, so again, this function here, it is proportional to this expression. Right? And this function, it is proportional here. Okay, I should write here, of course, beta over 2. And this function here, it is proportional to this expression, to this exponent, right? And so when I plug everything inside this integral, and when I take out of the integral the corresponding normalizing constants, corresponding to this distribution here and to this distribution here, I get inside the integral the exponent, so that here there is this quadratic form, right? Because the arguments of this quadratic form is given by this, and the argument of this quadratic form of this distribution is given by this. So very simple. Then what I do? First of all, this is the quadratic form inside this integral. Of course, we know how to integrate the how to calculate the integral of the exponent of the quadratic form. This is the standard calculations. Let me explain how we can do this in quite optimal manner. So this is the quadratic form. What we do, we introduce this matrix A, and also we introduce this posterior mean value. So remember that this is exactly the posterior mean value of the vector of parameters W, right? Here is it. This is the posterior mean value of this posterior distribution, of this predictive distribution. What I do? First of all, I subtract this posterior mean and add this posterior mean. And because this is a quadratic form, I can just open brackets and regroup the terms in such a way that here I get the same quadratic form, but now it depends only on this posterior mean. And this is the quadratic form which depends only on W. That's it. And so this is okay, and this is the value of the quadratic form here. So it is given by the same expression as here. The only difference is that here instead of W, I use this posterior mean. And so now this integral here, it is given by this expression, because, okay, this term doesn't depend on W, so I take it out of the integral. And here I get this expression with respect to W. But okay, this is the standard integral of the Gaussian, unnormalized Gaussian density. And because I know the exact expression for the normalizing constant of the Gaussian density, it is given by the determinant of the, it is defined by the determinant of the matrix of the quadratic form here. So I get this normalizing constant. That's it. And therefore, the evidence, actually this term, this thing, it is called evidence. So this is the evidence of the sample when I integrate out the unknown parameters with respect to the prior distribution. It is called evidence. And so this is evidence. Log evidence here is equal to logarithm of this big expression. And so here is it. where the value of matrix A is given by this expression, and the value of the vector of parameters omega m is given by this expression. And now what I do, I maximize this evidence with respect to parameters alpha and beta. What is interesting is that in this evidence function, nothing depends on W. And so this is a pure expression of alpha and beta, and I can estimate alpha and beta by maximizing this log evidence. Again, all the terms in this expression are defined by these formulas. And so we can estimate the model complexity also by maximizing the evidence. Why? It's because this evidence, it also depends on the number of the basis functions. The number of basis functions is given by the parameter m, and so I can actually maximize not only with respect to alpha and beta, but also I can consider different number of basis functions and select such model for which the log evidence, such number of basis functions for which this log evidence provides the highest value. And this is the standard, the standard approach. Any questions so far, guys?
Maybe one small question. And we maximized the evidence function just to get the values of alpha and beta for our we had to get the most probable values of alpha and beta, and we did that for that. Right?
Yes, exactly. And so what is the difference between frequentist approach? In frequentist approach, in standard machine learning, what we do, we take the validation sample, right? And we use cross-validation, and we maximize cross-validation error with respect to unknown hyperparameters, for example, with respect to the regularization coefficient, to estimate their most optimal values, and then we use these values of parameters, right? But here we don't extract any specific validation. We use the same sample both for tuning of parameters, for estimating the model, and also for estimating the hyperparameters, right? Because okay, this evidence, it is calculated on the same sample, and this is the difference. Okay.
Okay, thank you.
Now let me show how this works. In case of this very simple model, so this is a simple polynomial model. We minimize sum of squared residuals to construct this model. This is the case when we consider a model with only zero polynomials, so the best fit is just constant approximation. When we take a model containing a linear term, the best fit is given by linear regression. The best, of course, we see that when m is equal to 3, that is, we consider a cubic polynomial, the fit is very good. And in case we consider the polynomial of 9th degree, the fit is very bad. That is, the error on the train sample is 0, but the error on the test set is very big. And this is the standard thing. The error on the training set goes down with respect to the number of coefficients m, but the error on the test set with respect to the number of polynomial terms, it goes up quite fast. However, if we if we fix values of alpha and beta, and see how log evidence behaves with respect to the number of polynomial terms. So we consider a model with like 1 polynomial term, with 2 polynomial terms, with 3 polynomial terms, etc., etc. We observe that this log evidence has a clear maximum. And so using this approach, we can perform model selection. Of course, it's maybe not the best way for model selection, but this is a good illustration of the general Bayesian concept. Yeah, so Bayesian model selection. Let us illustrate how log evidence also depends on alpha and beta. We set beta to its true value, and we consider a polynomial model of order 9. So the polynomial model contains 9 non-zero polynomial terms. And here we plot dependence of log evidence with respect to alpha. And also we plot how test error of the model obtained for this specific value of alpha, how it looks like. And so we see that log test error is minimized with respect to this value of alpha, and log evidence is maximized with respect to almost the same value of alpha. So that means that log evidence is a good proxy for the error on the test set, how it behaves and how it behaves on unknown hyperparameters. Okay, that's it, guys. So I think that there are still 8 slides. On these 8 slides, there is some algorithm how we can optimize log evidence with respect to parameters alpha and beta. The algorithm is quite technical. So first of all, you will discuss some technical ideas of the optimization on the seminar. And also maybe the next on the next lecture, I will have some time. So I will explain you the technical ideas behind this algorithm, description of which starts from the slide number 41. But actually, this is not the main thing which we need to discuss today. I think we stop here and have a short break. Please spend some time at home to look through the slides. Technically, they're not difficult, and in principle, they're useful. So they still contain some useful details. Although I'm not sure that in practice you will need this particular algorithm to deploy for some specific application. You know, although as I said, the ideas are still maybe useful. Any questions so far? So again, let me stress. This is log evidence. This is the evidence. Of course, we can maximize the evidence using standard gradient descent, right? We calculate the gradient with respect to alpha. We calculate the gradient with respect to beta, and this can be done, you know, explicitly. But in this particular case, in case of a linear model, this is not the most optimal strategy, in the sense that for the linear model, some things can be written out more or less explicitly, and because of that, you can optimize evidence for linear model a little bit more efficient than you often do this in case of some general models. This is the only, you know, the only difference. And this is why I added to this presentation explanation of this particular algorithm, which works only for the linear case. Guys, any questions? Alexey, are you here? Alexey? Okay, so I think that we'll start in Nikita, are you here?
Yes, I'm here.
Okay, so when do we start the seminar? Like in 10 minutes, 15 minutes, what is the schedule?
Let's start in 15 minutes.
Okay, so we start at what? 10 minutes past 2, right?
Yes.
Okay,